All right, today we're cracking open one of the biggest unsolved cases in the entire cosmos, the black hole information paradox. This is a mystery that pits the two pillars of modern physics against each other in a fight to the death, and it threatens a fundamental law of reality itself. Solving it, well, that might just be the key to a theory of everything.
So, at the heart of this whole mystery is a really simple but profound question. Can the universe's ultimate instruction manual, the sum total of everything that makes a particle what it is, just be erased from existence? The laws of physics as we know them are screaming, no way. But our prime suspect says, oh yeah, watch me.
Now, when physicists talk about information, they're not talking about your latest text message, okay? They mean the unique quantum state of every single particle. Think of it like this. If you knew the complete information of every particle in a scrambled egg, you could, in theory, run the movie backward and unscramble it. Information is the actual blueprint of reality.
To solve this case, we've got to start where every investigation starts. We have to visit the scene of the crime, a place where the fundamental laws of the universe just seem to be broken.
This right here, this is the law that's supposedly being violated. It's a core principle of quantum mechanics, and it basically says you just can't create or destroy information. It's a cosmic conservation law. Whatever goes into an interaction has to come back out. It might be scrambled, sure, but it has to be complete.
And here's our suspect, the black hole. See, according to Einstein's theory of general relativity, a black hole's gravity is so intense that once anything crosses its boundary, the event horizon, it can never, ever escape. So what happens to the information of the star or the dust or the unlucky astronaut that falls in? It just seems to be gone forever.
And the paradox, the whole reason we're talking about this, is because this cosmic crime scene forces the two greatest theories of the 20th century into a head-on collision. This is a heavyweight title fight for the soul of physics.
So the whole problem boils down to this clash. On one side, you have general relativity, our theory of gravity and all the big stuff, which builds this perfect prison for information called a black hole. But on the other side, you have quantum mechanics, our theory of particles and all the tiny stuff that absolutely insists information can never be imprisoned forever. One of these theories, as they stand, has to be wrong, or at the very least, incomplete. You know, this waterfall analogy really is the perfect way to think about an event horizon. It's not some physical wall you'd bump into. If you were falling into a black hole, you wouldn't feel a thing. It's more like being in a boat caught in a current that's getting faster and faster. At some point, the water is moving faster than your boat can go. You've crossed the point of no return, even if you don't realize it yet. The event horizon is a place, not a thing. So, for decades, this whole thing was kind of a theoretical headache. But then, back in the 1970s, Stephen Hawking made a discovery that turned it from a headache into a full-blown raging paradox. Let's walk through this, because it is absolutely brilliant. Hawking realized that if you apply the weird rules of quantum mechanics to the space right at the edge of a black hole, these little virtual particle pairs are constantly popping into existence. And every so often, one partner falls in, while the other escapes. That escaping particle? That's Hawking radiation. It carries away a tiny bit of the black hole's energy, causing it to shrink, and over trillions of years to evaporate completely. And this is the bombshell. If the prison itself, the black hole holding all that information, eventually just vanishes, what happened to all the blueprints it swallowed? Hawking's math showed the radiation was purely thermal, basically random heat, like what comes off a toaster. It carried no useful information about what fell in, so it looked like the original information was just deleted from the universe. And just like that, the paradox was born. Okay, so this paradox sent physicists absolutely scrambling. For the last 40-plus years, they've been searching for clues, proposing some truly mind-bending ideas to try and solve the case of the missing information. Let's take a look at the investigation file. Man, this investigation has had some wild twists. In the 90s, you had ideas like complementarity, this weird concept that information is both inside the black hole and on its surface at the same time. It just depends on who's looking. Then came the even more radical holographic principle. But that led to its own set of problems and gave rise to the pretty terrifying firewall theory that maybe the event horizon isn't a peaceful crossing, but a deadly inferno. So out of all these ideas, the holographic principle really took hold and became this profound new way of looking at physics. The idea is that our 3D reality is kind of like a hologram, an image that's projected from information stored on a 2D surface. In this view, information never actually falls into the black hole. It gets smeared out and imprinted on the event horizon, and that's what gets slowly encoded in the escaping Hawking radiation. Problem solved. Information saved. But the debate just kept on raging. The firewall idea seemed to punch a hole in even the holographic solution. The case went cold. That is, until 2019, when a brand new, absolutely electrifying clue emerged that might just change everything. So, this new lead comes from some incredibly complicated math, but the basic idea is surprisingly simple. It suggests that the boundary between the inside and outside of a black hole isn't some clean, perfect line. What if, instead, parts of the inside are fundamentally connected to the outside?
So, say hello to entanglement islands. The theory goes that these are tiny pockets of the black hole's interior that are quantum mechanically linked or entangled with the Hawking radiation way outside the black hole. That means their fates are tied together. What happens to a particle inside the island is instantly reflected in a particle outside. It's a bridge, a way for information to escape from what we thought was an inescapable prison.
And here is where it gets truly wild. For a supermassive black hole, researchers calculated that these islands could actually extend beyond the event horizon. We're not talking by much, only about the width of a single atom. But that tiny distance makes all the difference in the world.
So why is an atom's width such a huge deal? Because it means this new physics isn't hidden behind that point of no return anymore. It means, with some futuristic super technology, you could theoretically send a probe to that region, measure the island, and then come back out. We could actually get hard evidence. The information isn't lost for good. It's just really hard to get to.
And so our cosmic mystery isn't quite closed yet, but we have our strongest lead in decades. And it leaves us with this incredible thought. The key to uniting gravity and quantum mechanics, the theory of everything, it might not be locked away in some unknowable singularity. It might be hiding just an atom's breadth away, in tiny little islands on the very edge of space-time.